You know, there's something truly magnificent about watching molten steel transform into the backbone of our modern world. Here at Sorel Forge in Quebec, Canada, they've been perfecting the ancient art of forging since 1902 and what you're seeing isn't just metalworking, it's engineering poetry in motion. These aren't your grandfather's blacksmith projects. We're talking about forgings that can weigh up to 300 tons. Pieces so massive, they make a pickup truck look like a toy. Sorel specializes in open die forging, a process that's remained fundamentally unchanged for over a century, yet somehow gets more impressive with modern precision. Watch as this 200,000-pound hydraulic press applies over 16,000 tons of force. The ingot, heated to a glowing 300 degrees Fahrenheit, is carefully manipulated under computer-controlled hammering. Each strike is calculated, reshaping the crystalline structure of the steel grain by grain. This isn't just about shape, it's about creating metal with superior strength and durability that you simply cannot achieve through casting. The forge masters here work like conductors of an industrial symphony. They're producing critical components for oil drilling platforms in the Gulf of Mexico, turbine shafts for power plants that light up entire cities, and pressure vessels for refineries. These pieces must withstand extreme pressures, corrosive environments, and decades of service without failure. What really takes you back is realizing this craft connects us to metalworkers from centuries past, just supersized for the industrial age. The principles remain timeless: heat, hammer, and human expertise. Sorel Forge represents that beautiful intersection where old-world craftsmanship meets cutting-edge metallurgy, forging the literal foundations of American industry, one massive piece at a time. Remember when turning a piece of metal on a lathe meant standing there for hours, manually adjusting dials and hoping you didn't mess up? Well, let me introduce you to DMG's monoblock CNC lathe, a machine that would seem like science fiction to the craftsmen of yesteryear. The monoblock's foundation is, quite literally, revolutionary. Instead of bolting separate components together like traditional lathes, the entire machine bed is cast as a single piece of mineral composite material called granitan. This isn't just any concrete. It's a proprietary blend that dampens vibrations 10 times better than cast iron. Why does that matter? Because when you're cutting metal at thousands of RPM, even microscopic vibrations can ruin precision. The heart of this beast is its direct drive spindle motor, capable of spinning at 6,000 RPM while delivering massive torque. There's no belt, no gears, just pure electromagnetic power. The tooling turret holds 12 different cutting tools and can index to any position in less than a second. It's like watching a master craftsman's hands, except these hands can repeat the same movement to within 0.0001 inches, thousands of times without fatigue. Here's where it gets really interesting: the control system. DMG's Siemens-based CNC controller doesn't just follow programmed paths, it thinks ahead. Using something called intelligent feed rate optimization, it automatically adjusts cutting speeds based on material hardness, tool wear, and thermal expansion. The machine is literally teaching itself to cut better. The coolant system deserves mention too. High-pressure coolant jets, we're talking 1,000 psi, blast directly at the cutting edge, washing away chips while cooling the tool and workpiece. This extends tool life by 300% compared to flood coolant systems from the 1990s. What really takes you back is watching this machine work. The cutting tool dances across the spinning workpiece with balletic precision, peeling away ribbons of metal that curl and break exactly as programmed. It's manufacturing poetry. Now here's a manufacturing process that really revolutionized foundation work, and it's fascinating to see how they pull this off. ICP, that stands for Internal Centrifugal Production, represents one of the cleverest applications of physics in concrete manufacturing you'll ever witness. Picture this. We're making pre-stressed concrete piles that'll be driven deep into the earth to support bridges, buildings, and infrastructure across America. But unlike traditional methods, this process uses centrifugal force, the same principle that keeps you pressed against the wall on a carnival ride, to create extraordinarily dense, strong concrete. The operation starts with a steel cage of pre-stressed tendons, pre-tensioned to about 70% of their ultimate strength. This cage is placed inside a massive steel mold, typically 40 to 60 feet long. Here's where it gets interesting. Fresh concrete is poured into this mold while it's spinning at roughly 400 to 600 RPMs. That's about 10 rotations every second. As the mold spins, centrifugal force pushes the concrete outward against the mold walls with tremendous pressure. We're talking forces equivalent to 50 times gravity. This does something remarkable. It compacts the concrete far beyond what vibration alone could achieve, squeezing out excess water and air voids. The result? Concrete with compressive strength exceeding 8,000 psi, significantly stronger than your typical foundation. The spinning continues for about 8 to 12 minutes until the concrete sets up. What emerges is a hollow core pile with walls so dense they're practically impermeable to water. Back in the day, we'd have needed much thicker, solid piles to achieve comparable strength. The beauty of this method, perfected over decades, is its efficiency. These centrifugal piles use 30% less concrete than solid alternatives while maintaining superior load-bearing capacity. They've been supporting American infrastructure since the 1950s, a testament to engineering ingenuity that never gets old. This is where precision metalworking reaches its absolute pinnacle. You're looking at the VDF Behringer 450-4 TCM horizontal mill turn machining center, and it's tackling one of manufacturing's toughest challenges: complete crankshaft machining. Crankshafts are the heartbeat of every engine, converting linear piston motion into rotational power. But machining one requires tolerances measured in microns. That's thousandths of a millimeter. This German-engineered marvel handles shafts up to 15 feet long and weighing several tons. Watch how the workpiece rotates while multiple tool heads simultaneously mill, turn, and drill from different angles. This 4-axis configuration means complex journal surfaces, bearing seats, and oil passages are machined in a single setup. Back when your dad was working, this job required 5 different machines and multiple repositionings, each one introducing potential alignment errors. The TCM technology tool centering measurement continuously monitors tool wear and automatically compensates. The machine maintains tolerances within 5 microns across the entire shaft length. For perspective, a human hair is about 75 microns thick. There's something reassuring about watching steel cable being born, knowing this is what holds elevators, suspends bridges, and lifts heavy loads safely every single day. This wire rope manufacturing process is pure American industrial ingenuity. It starts with individual steel wires, each drawn through dies to exact specifications, typically 0.020 to 0.200 inches in diameter. These wires are then twisted into strands using a closing machine. Watch carefully. 6 wires spiral around a center core wire, creating a strand with inherent strength and flexibility. Next comes the rope laying operation. Multiple strands, usually 6 or 8, are helically wound around a fiber or steel core. This multi-layer construction is brilliant. It distributes load across hundreds of individual wires, so if one breaks, the rope maintains integrity. The pitch and direction of the lathes are precisely controlled to prevent unwatchful rotation under load. Now here's a technique that goes back to sailing ship days, the Flemish eye splice. This creates a permanent loop in the cable end without using clamps or hardware. The rope end is unlaid. Individual strands are tucked back through the main rope body in a specific interwoven pattern, typically 5 full tucks per strand. Each tuck locks the previous one, creating a splice that's actually stronger than many mechanical fittings.